The National Electrical Code, or NEC, does not explicitly address the ampacity of conductors installed in two duct banks for 21 kV feeder circuits. However, based on the ampacity values provided in Table 310.78, it is reasonable to interpolate between the values for one duct bank, which is 305 amps, and three duct banks, which is 245 amps. Using linear interpolation, the ampacity for conductors installed in two duct banks would be approximately 305 amps minus the quantity of 305 amps minus 245 amps multiplied by the quantity of 2 minus 1 divided by 2, which equals 275 amps. Therefore, for a 350 cm conductor in a 21 kV circuit installed in two duct banks, the ampacity would be 275 amps. Regarding the insulation rating of equipment ground, the NEC does not explicitly specify the insulation rating of equipment ground conductors for systems operating at 1 kV or higher. However, based on the requirement for 600 volts insulation for neutral conductors in solidly grounded systems as described in NEC section 250.184a, it is reasonable to assume that equipment ground conductors should also have an insulation rating of at least 600 volts. Let's delve deeper into the NEC requirements and industry best practices for ensuring safe and compliant high voltage installations. We will first address the ampacity considerations for conductor installations in duct banks, and then discuss the appropriate insulation rating for equipment grounding conductors in high voltage systems. When determining the ampacity of conductors in duct banks, it is essential to consult the relevant tables and figures in the NEC. Specifically, Article 310.60 covers ampacity of conductors rated 2001 to 35,000 volts. Figure 310.60 illustrates various duct bank arrangements for use with tables 310.77 through 310.86. These tables provide ampacity ratings for different conductor sizes and insulation types based on the number of circuits in the duct bank and the ambient temperature. As you noted, Detail 1 illustrates one duct bank, and Detail 2 illustrates three duct banks. The NEC provides ampacity values for these specific configurations. However, when dealing with two duct banks, as in the given scenario, direct ampacity values are not explicitly provided. In such cases, it becomes necessary to apply engineering judgment and consider the specific installation conditions to determine a suitable ampacity rating. As a starting point, the linear interpolation method can be used as you demonstrated. This method provides a reasonable estimate of the ampacity based on the values for 1 and 3 duct banks. However, it is crucial to remember that linear interpolation is an approximation and may not always accurately reflect the actual ampacity due to factors such as variations in soil thermal resistivity, duct bank spacing, and conductor bundling. To further refine the ampacity calculation, consider the following factors. Firstly, soil thermal resistivity. The thermal resistivity of the soil surrounding the duct bank significantly affects the heat dissipation from the conductors. Higher soil thermal resistivity results in higher conductor temperatures and reduced ampacity. Therefore, it is essential to obtain accurate soil thermal resistivity data for the installation site. Secondly, duct bank spacing. The spacing between the duct banks influences the amount of heat that can be dissipated from each duct bank. Closer spacing reduces heat dissipation and lowers ampacity. Ensure that the duct banks are spaced adequately to allow for sufficient heat dissipation. Thirdly, conductor bundling. If multiple conductors are bundled together within a duct, the heat generated by each conductor can affect the temperature of the adjacent conductors. This effect is known as mutual heating and can reduce the ampacity of the conductors. The NEC provides adjustment factors for conductor bundling, which should be applied accordingly. Fourthly, ambient temperature. The ambient temperature surrounding the duct banks affects the conductor temperature. Higher ambient temperatures reduce ampacity. Obtain accurate ambient temperature data for the installation site and apply the appropriate temperature correction factors. Fifthly, conductor insulation. The type of conductor insulation affects its temperature rating. Conductors with higher temperature ratings can operate at higher ampacities. Ensure that the selected conductor insulation is suitable for the operating temperature and voltage of the circuit. To determine the most accurate ampacity rating for two duct banks, it is recommended to consult with a qualified electrical engineer who can perform a detailed thermal analysis of the installation. This analysis can take into account all the relevant factors and provide a more precise ampacity rating than linear interpolation alone. Now let's discuss the insulation rating of equipment grounding conductors in high voltage systems. The NEC provides specific requirements for grounding systems in Article 250. Section 250.184 addresses the insulation level for neutral conductors in solidly grounded systems operating at 1 kV and over, stating that the minimum insulation level shall be 600 volts. While the NEC does not explicitly specify the insulation rating for equipment grounding conductors in high voltage systems, it is generally accepted industry practice to use conductors with an insulation rating of at least 600 volts for this purpose. This practice is based on the following considerations. Firstly, safety. Equipment grounding conductors provide a low impedance path for fault current to return to the source, thereby minimizing the risk of electric shock and equipment damage. Using conductors with adequate insulation helps to prevent unintended ground faults and ensures the integrity of the grounding system. Secondly, coordination. The insulation rating of equipment grounding conductors should be coordinated with the insulation rating of the phase conductors and neutral conductors in the system. This coordination ensures that the grounding system can withstand the same voltage stresses as the other conductors in the system. Thirdly, code compliance. While the NEC does not explicitly require 600 volts insulation for equipment grounding conductors in high voltage systems, many local jurisdictions and project specifications do. Therefore, it is essential to check with the local authorities and project requirements to ensure compliance. In addition to the insulation rating, it is crucial to select equipment grounding conductors that are properly sized to carry the available fault current. The NEC provides guidelines for sizing equipment grounding conductors in Section 250.122. The size of the grounding conductor should be based on the size of the overcurrent protective device protecting the circuit. Furthermore, consider the material of the equipment grounding conductor. Copper and aluminum are the most common materials used for grounding conductors. Copper has a higher conductivity than aluminum, but it is also more expensive. Aluminum is lighter and less expensive than copper, but it requires larger conductor sizes to achieve the same conductivity. The choice of material depends on factors such as cost, weight, and conductivity requirements. Shielding of conductors operated above 2000 volts is addressed in NEC section 310.6, and you are correct that all 21 kilovolt MV cable typically has shielding. The purpose of shielding is to contain the electric field within the cable insulation and to provide a path for fault current to return to the source. However, equipment grounding conductors are not typically shielded. The primary function of the equipment grounding conductor is to provide a low impedance path for fault current, not to contain the electric field. In summary, when installing 21 kV feeder circuits, it is essential to carefully consider the ampacity of the conductors and the insulation rating of the equipment grounding conductors. While the NEC does not always provide explicit guidance for every scenario, it is possible to use engineering judgment and industry best practices to ensure safe and compliant installations. Remember to consult with qualified electrical engineers and local authorities to ensure that all applicable codes and standards are met. By adhering to these guidelines, you can minimize the risk of electrical hazards and ensure the reliable operation of your high voltage systems.